Today I'm compressing a 1.5 day presentation into a 1 hour, and also I think I can cover only up to the air termination, down conductors, and separation distance. And if we have time, we'll go into the earthing systems, or we'll take it up in a separate webinar. And I also plan to give a brief overview, a critical overview of alternative air termination systems. Now you all know that when it comes to lightning protection, we look at the lightning protection in two distinctly different scenarios: protection of structures and protection of equipment. Although apparently they are distinctly different, actually they come in one package when we go into the lightning protection as a turnkey project. And a structural protection system has basically two parts: what we call external protection system, which has air termination, down conductor, and earthing system. So simply, the air termination will interact with lightning. Down conductor brings the lightning current from the roof level to the ground level, and the earthing system will dissipate the charge brought in the lightning current into the surrounding soil. And apart from that, we have internal protection system. That is, either we bond the metallic parts into the lightning protection system to avoid arcing, or we keep them separated by a certain separation distance. When we are connecting, there are two ways of connecting. One is direct connection, and other one is connection via surge protective devices, or we call it transient bonding, which is not the topic for today. So that I'm sure that most of you know that these are the main parts of a lightning protection system, which I told you. And then we are going to a very important point. Unfortunately, we are not going to the details of this. When we are giving lightning protection, somebody might ask, okay, there is a hospital in a very lightning dense area. For an example, in India, imagine that in Guwahati or in Bhubaneswar, where the lightning density is quite high, a building, a hospital that houses 4,000 people is there. And there is another structure, a small dwelling in a desertic area. Say, for an example, in Iran, in Tehran, where the lightning density is quite low. Are these two buildings given the same level of protection? If it is the case, then it is not engineering, because we know that in the name of engineering, what we do is optimize the resources that we have. Therefore, when we give lightning protection systems, we conduct something called the risk assessment. And by this risk assessment, we get an idea whether a building is needed protection, whether we have to give the protection to the building, and if it is needed, up to what level we have to give. And that part, the risk assessment of lightning protection, is a separate subject. It's not a separate subject, but it is a separate subject to be taken in a workshop or training program, because it is usually a one-day training program. So therefore, I'll keep it aside I'll take the outcome of the final risk assessment, which is given in terms of levels of protection. Level 1 is the highest level of protection, which we will give to, say, something like power stations, hospitals, very high risk installations in very high lightning dense areas. And level 4 is the lowest level, which we give in low lightning density areas and less significant buildings. And then when we define the withstandability of the lightning protection system, we say that if depending on the level of protection, the lightning protection system can withstand, and the lightning protection system is effective for a maximum and minimum current. That means if you take level 1 protection, the maximum current that this system can withstand is around 200 kiloamperes. And if it is the other end, it is 100 kiloamperes. What does this mean? What that means is, if, for an example, in the level 1 protection, you have certain number of conductors, and this number of conductors is designed in a way that it can withstand up to about 200 kiloamperes. If the current exceeds that, there is a possibility that the components of the lightning protection system may fail. So this is what is meant by maximum value of current. And there's a minimum value as well. What does that mean? It says what is the minimum current that a given lightning protection system can interact with. That means if, say for an example, if you apply level 3 protection, and if a lightning comes of which the maximum current is less than 10 kiloamperes, there is a chance that this lightning may be missed by the upward leader. When Sri covers the basics of lightning, you will understand what is an upward leader or upward answering leader from air termination system. It may miss the step leader and the lightning may get attached to an unprotected part of the building. And the standards say that these are the possibilities, or these are the percentage of success in the case of each level of protection in lightning protection systems. For an example, if you are going for level 3 protection, 95% of the cases, the system can withstand the lightning currents, and 91% of the cases the system will interact with the lightning. And most people understand the first thing, the maximum current, but many people do not have a good idea about the minimum current. Therefore, let me show it graphically. Now consider that there is a lightning coming, and say that if the peak current is high, something like 100 kiloamperes. Now when this lightning is coming, okay, now you see that if the lightning has a very high current, that means it is bringing very high charge. It is bringing down very high charge. Therefore, when the lightning step leader is approaching to the building, at a very early stage, our air termination system will send the answering leader, so that it is much easier for the lightning to get attached to the air termination. Let me show you that again. Okay. Now consider that if the peak current of the lightning stroke is low, say like 5 kiloamperes, now you can see what happens. Okay, now you will see that before the answering leader is started from the air termination system, the lightning itself, the step leader will go down, and by the time the streamer is propagated from the air termination, it has already been attached to an unprotected part of the building. So that's why we define a minimum current that the lightning can interfere with. And there are three ways of implementing air termination. Now you know that in order to capture the lightning, the word capture is not very correct. The usual word we use, scientifically correct word, is intercept, because the lightning protection system is not to catch or attract lightning. It is to intercept with lightning. And we have three methods. One is called the mesh method. Another one is called the protective angle method. That means we have a vertical air termination and there is a cone of coverage from that. And the third one is called the rolling sphere method, where a sphere, an imaginary sphere is rolled around the building, and wherever the sphere touches, we need an air termination. And the easiest method to explain is the mesh method. And it is the most expensive as well, because we need a lot of material. And when we are preparing the mesh, if it is level 1 protection, our mesh size is quite small. That means we need a lot of material. And as we go down the line, the mesh size increases. That means the dimensions or the material will also decrease. And when you are having the mesh method, you have to keep you have to pay some careful attention that always you have to cover the roof ridge lines, roof overhangs, and roof edge lines. And as a rule of thumb, we say that in a building like this, if y over x is less than 0.1, the ridge needs a mesh conductor at the edges, the roof edges as well, apart from the roof ridge. And these are the cases where you need lightning. What you see from one is the places where you essentially need the conductors, the air termination conductors, and number 2 shows where you may or may not need the air termination. And few diagrams, I will run this quickly. And then we go to the protective angle method. It looks simple. We have an air termination, and there is an angle, a certain angle by which we can think that the building is protected. And just to show it graphically, sometimes you need 1 air termination, sometimes you need 2 air terminations, and few diagrams. And this table shows you what is how we are calculating or how we are determining the protective angle. Now you see that this is directly from IEC 623.053 2010. This curve shows how the angle changes with the height of the building and with the level of protection. Now, for an example, if we have an air termination, the tip of which is having a height of say 30 meters, and if we are applying level 3 protection, so the protective angle is somewhere around 36 or 37. Okay, and there is one very important catch point of this table. Now you see the H, the x-axis H, is height of air termination above the reference plane. So keep in mind that it is not the height of the building. It is the height of the air termination above the reference plane. What is the reference plane? Let me explain you it in the next slide. Okay, now consider that there is a building and we have an air termination. Let me take the right-hand side air termination. Now you can see that if we consider the rooftop of the building, imagine that we are going to protect something on the rooftop of the building. Now the reference plane will be the rooftop, which I call reference plane 1. And therefore you get an angle alpha 1. If you refer that table I showed you earlier, you will understand that. Let me go back and come. If the height is smaller, as you go towards the left-hand side, the height is smaller, the angle is larger. Okay? And let us go back to this. So if you take something to be protected on the rooftop, then your H should be H1. So the angle is alpha 1, which is a larger angle compared to if you want to protect something at ground level, then the reference plane will be ground level and your angle is now smaller. It is alpha 2. So for the same level of protection, you have two different angles of protection. And now let me show you a few diagrams. Let me go faster. Okay, so now you see that the same thing I explained you. If you want to protect something like this is a 2D diagram, so be careful. If it is a 3D, then it is a solid angle, not just a simple angle. The edge of the part to be protected should be inside this protected volume. And then somebody might ask how I know the area to be protected and what would be the radius to be protected. Now for an example, say that this is the plan view of a building. The view when I look from look from above the building, and imagine that I am going to have air termination at the middle. Now, what is the distance in terms of X and Y that should be protected? It's very simple. For this case, it is simple. So if I protect the edge of the building, one of the edges of the building with radius R, then can you see that I'm protecting the entire building? Okay, now what would be R? You can very simply see that it is x squared over 4 plus y squared over 4 square root. Likewise, I have removed all the other slides to save time. Depending on where you are placing the air termination system, we can derive an equation in the same manner. And this table also is very important, and you can't see it very clearly, but it gives this table on the right-hand side is given in the tabulated form in the left-hand side table, and it is, today we don't have time to go to an example to work out, then you will find that this table is much more handier or smarter than the diagram in the right-hand side in calculating a real case. And then we go to the rolling sphere method. Now imagine that we have a building, and we forget about, I forgot to erase this green color air termination. Say that we roll a certain sphere, imaginary sphere, on this building, the top of the building, and let me say that I put two air terminations at the two edges, the brown color air terminations. Forget about this green color one, it is mistakenly appearing. And when you settle, when you rest this imaginary sphere on the building, don't forget that this is a 2D picture, and as the sphere touches the air terminations, if it is not touching the building, say that it is few millimeters above the building, then we say that the building is protected. This is the rolling sphere method principle. Now, how to determine R? The standards give the values of R. Now you can see that similar to the protective angle method, in the rolling sphere method, as you go down the line, the rolling sphere radius increases. What does that mean? If you have a smaller rolling sphere radius, then you need more air termination or taller air terminations to prevent the rolling sphere from touching the building. So that means you need more material. But as you go down the line, for higher levels of protection, you need smaller amount of material. And now, say for an example, this sphere is at level 3. So its radius is 45 meters. But what happens if we go one level up, 30 meters? That means a smaller sphere. Now, you will find that the sphere will touch the building because now it is getting into in between the air terminations. What have we got to do? So you can see here that it is touching the building. What we have to do is now we'll increase the size of the air terminations so that the smaller sphere can now still rest on that without getting the touch on the building. Or alternatively, what you can do is to, instead of these two the green color extensions, you have a third one in the middle of the building, so that still it will not touch the building because it will touch the air termination. Okay, now we are coming into some important points. Now you see that in this particular case, when you roll the air termination, when you roll the air termination, when you roll the rolling sphere, it will touch the building only at the roof top level. So therefore, you have to protect only the rooftop level. So air terminations are needed only at the rooftop level. Okay, now let's see a case where the rolling sphere touches the building the sides of the building before it touches the top of the rooftop. Now the standards say that even if the sphere touches the sides of the building, still the height of the building is less than 60 meters. Okay, if the building height is less than 60 meters, you need to have air terminations only at the roof level. Let me repeat. Even if the rolling sphere touches the sides of the building, if the building height is less than 60 meters, you don't need to protect the walls. You have to protect only the rooftop of the building. So that is what the standards say. So in other words, you need to protect only those areas which are now you are seeing. Okay, now we are going to the case where your building height is greater than 60 meters. Now what they say is that if the building height is greater than 60 meters, you have to protect not only the rooftop level, but you have to protect with air termination down to a level which is 20% of the height of the building. In other words, you have to protect by mesh method the part of the building above 80% of the height. Now, say for an example, if you have a building of height 100 meters, then apart from the rooftop level, you have to protect with air terminations up to 80 meters of the building. Now you can see that it in this diagram. So that if the building is 100 meters high, you have to protect up to 80 meters. And then if there are any protrusions on the sides of the building, you have to have an air termination and protect that as well. So this is how you can protect such protrusions if the rolling sphere is touching it. And then we are coming to a very important point. You can protect your building with natural components. What does that mean? Natural components means not something happens naturally, but any component of the building which is not meant for lightning protection, but meant for some other purpose. For an example, roof of a building. Say that you have tin roof building or corrugated iron roofed building, or you have a tank on top of the building, a metal tank. Those things you can use as your lightning protection system, provided that it satisfies these conditions. Let me go to the rightmost column. Thickness T dash in millimeters. If your building is not housing any flammable material, then the thickness of the roofing material is what in that column you need, the minimum thickness, to consider that as the air termination system. For an example, if you have a factory with corrugated iron sheets and say that they are galvanized steel, and if the thickness of the steel sheets is more than equal or more than 0.5 millimeters, and if the building is not housing something like fabrics, petrochemicals, gunpowder, something like that, which is inflammable, then you can use that roof itself as the air termination. So you don't need any copper tapes or anything up above. But on the other hand, if there are materials that are inflammable or explosible, then the thickness should be much higher to be treated as the air termination itself. Like if it is steel, it should be 4 millimeter thickness. Let me show you some pictures, you will understand then. Now, this is a factory with galvanized iron roof that stores steel products. Now, if the thickness is 0.5 millimeters or above, you can use it as a steel reinforcement, the air termination. What you simply need is to earth that. Now you see structure with steel roof that houses explosives. Imagine that this is a explosive storage. Now, if you are considering these roof materials as air termination itself, it should have at least 4 millimeter thickness. The same thing in the case of fixed roof naphtha or petrochemical tanks. Don't forget that I'm repeating, this is applicable only to fixed roof petrochemical tanks, not applicable to floating roof petrochemical tanks. And if it is fixed roof, and if you can ensure that there are no fumes escaping from this tank, you can use it itself as the air termination if the thickness of the material is more than 4 millimeters, more than the specified thickness of the material. And embedded LP is not recommended for floating roof type storage. Keep that in mind. I am emphasizing it. And also another important point. When we analyze the lightning data, we find that more than 90% of lightning strike damages occurred at upper corners and ridges and facades of a building. We have statistics from Malaysia, from USA, from Singapore, and there are some data from China. And all this data shows that 90% of the lightning strikes ends up at these points shown by yellow color arrows and lines. And less than 5% occurs on vertical edges below the top, like these points. And less than 1% occur on flat surfaces, either horizontal or vertical, like these places. So what does that mean? If your building is struck by lightning, then there is a fairly high chance that the lightning get attached to the corners and edges. Therefore, when you're implementing your air termination system, make sure that you protect edges and corners. And then we are going to the down conductors. So when you are implementing down conductors, make sure that there are several parallel current paths. It's quite dangerous to have single down conductor. The usual recommendation is that always you need 2 down conductors, and length of the current path is kept to a minimum. So have your down conductor as straight as possible. Don't make it going through a bent route with a lot of bends and change of direction. And also, as far as possible, try to get the down conductors as a direct continuation of the air termination system. And then the standards give the maximum separation between, not maximum, the optimum separation between down conductors. So now be little cautious about these values. What they mean is that actually, if you have a building with perimeter 100 meters, okay, perimeter 100 meters, and if you have, if you are going to implement level 4 protection to the building. So for level 4 protection, the separation is 20 meters. So now this table will help you to find how many down conductors you need, how many minimum number of down conductors. So it is 100 divided by 20, which is 5 down conductors. Now, there is no hard and fast rule that you need to put these 5 down conductors exactly at 20 meter separation. That will put you into hell of a lot of problem, because if you start from a nice plain wall, then you will find that one down conductor will go across a window, another down conductor go across a door, and that will be a mess. Therefore, the idea is that now once you determine the number of down conductors, you place it as separated as possible, but avoid any inconvenient places and places where somebody might touch the wall, okay, or somebody might touch the termination. So that don't stick to this separation itself, be little practical. And then the usual practice and usual recommendation is, if you have a building more than 20 meters, it's better to connect the down conductors by another conductor horizontally, which we usually call ring conductors, at every 20 meters. Okay? And now you see that this is a building, for an example, greater than 60 meters. Now you see that the top part of the building, in the rooftop, you have the air termination. Then up to 20% of the building height, you have a mesh. And below that, every 20 meters, there is a ring conductor. This is the typical practice that we adapt. And also, you can use the natural components for down conductors as well. And the most common natural component that you can use for down conductors is the reinforcement structure of the building, the steel reinforcement. However, when you're using the steel reinforcement, there are 3 conditions you have to satisfy. What are they? 50% of interconnections of vertical and horizontal bars should either be welded or securely tied. Now, in the civil engineering standards, there is a problem of welding. Therefore, securely tied is the better way or the practical way you can do it. Then vertical bars are overlapped a minimum of 20 times their diameter. Actually, if I had face-to-face interaction, I could have very nicely shown you how to do this, but I think you can understand it. Then the third one is, from top to bottom, the resistance between the topmost point of the reinforcement steel structure and that at the ground level should be less than 0.2 ohms. Usually you can achieve this without much trouble. And then this is the place where you are always getting some clashes with the civil engineers. you have to, if you're using the steel reinforcement structure as your down conducting system, still you have to take the continuity of the steel reinforcement out of the building at the top and at the bottom to be connected to the air termination and the down conductors. And most often the civil engineers are really pissed off when you say that you want to do that. Unfortunately, the lightning protection standards and civil engineering standards are not very friendly. They have not been matched so far, which I'm raising at each and every conferences and meetings that we have to do this. Maybe in the future we can come to some sort of compromising in this regard. And some people, as they find little difficult to practically fulfill those three conditions, they recommend having a mesh of additional tapes, maybe copper tapes, maybe aluminum tapes, maybe some other type of tapes, GI tapes, connected to the steel reinforcement bar. So you can't see these tapes from outside. They are together with the steel reinforcement, and then use it as the the down conductor system. Now the advantage is you are having a separate down conducting system in addition to the steel reinforcement. And then there are many questions of what material to be used. I think there are some arguments, even Mr. Gopakumar and I have some differences in this case, where my research shows that you can use GI tapes as well. And I recommend GI tapes more than copper tapes because at the moment, there are some conflicts between the standards as well. My research students found that there is no problem of having GI tapes, and copper tapes may have some more problems. But some people say that you can use copper tapes. We can have a separate discussion in this regard. Okay, but be careful if you're having your down conductors or air terminations on a roof or wall material which is also metal. If the materials are not compatible triboelectrically, there may be serious corrosion in between the air termination and the down conductor and the roofing or walling material. So what you see here is a serious corrosion that has been taken place when copper tapes are aligned on iron roof material. And also don't lay your down conductors close to windows where somebody might touch it accidentally during a lightning strike. And also there is a chance of arcing into the metal parts. And also there is a serious concern about this. Sometimes we need insulated cables, insulated conductors to avoid, especially to avoid triboelectric effect. That means corrosion between the lighting protection system and the building material. But if you are using insulated cables or insulated pipes to avoid arcing from the lightning protection system to the metallic parts, be little careful. If the conductor is very tall, very long in length, there may be a chance of arcing, damaging the insulation material and having the arc into the metal. What you see is an insulated cable which ran from top of a communication tower. This is in Sri Lanka, to down, and separating the down conductor with this insulator from the the steel bars, rebars of the tower. You can see that around 80 meters above the ground level, there are so many arcing and damage of the insulator. And then we come to equipotential bonding. Equipotential bonding can be either direct bonding or transient bonding. What do you mean by direct bonding? In order to avoid arcing between the lightning protection system and any other metallic part, you have to connect them directly so that the current will flow through the connecting wire. If it is dangerous, if you don't like the lightning current to get into your premises, then you can have a separation distance. We are going to see how the separation distance is calculated in the next few slides. And sometimes you can bond them only during the lightning current. We call it transient bonding. So that this is usually done when you want to connect, say for an example, power earthing system and the communication earthing system, which are not favorable to be connected under normal operating conditions, but should be connected under lightning or transient conditions. And if it is separation, if you're keeping a separation distance, then there is an equation which is used to calculate the separation distance. We are going into that next. Okay, before going to the separation distance, when you are connecting the lightning protection system and other metallic components, these are the values which we usually give for the cross-sectional areas of the tapes which we are using for different purposes or at different places. Okay, now we are coming to the separation distance. When we want to keep a distance between the lightning protection system and any other object nearby, we have to make sure that we are keeping a minimum distance between them. And this minimum distance is calculated by this equation where Ki, Kc and Km are the constants of which the values are given in the next few slides. And L is the distance from the point of possible arcing in the lightning current path to the equipotential bonding level. Let me show you that in the next few slides. And okay, these are the values given in the standards. Ki depends on the level of protection, class or level of protection. And Kc depends on the number of down conductors, but Kc is a little complex constant than this in some cases. I will show you later. But if you have very simple single down conductors, then depending on the number of down conductors, you can get your Kc value. And Km, not unfortunately, but due to the scientific limitations, Km is defined only for air and concrete at the moment. So Km is the material. It depends on the material in between the lightning current path, that is a down conductor, and the object to which there can be an arcing from the down conductor. So it is for AI, it is 1 concrete 0.5. Now let me take an example. Consider that there is a lightning protection system or the down conductor going, taking the double bends on a building. And if a person is moving there or standing, then the maximum height the person gets is usually when he lifts his hand, isn't it? And then we assume that the height will be about 2.5 meters. If a person is 2 meters, then when he raised the hand, it's about 2.5 meters. And then you will get a certain distance D. And now this down conductor with the double bends is allowed only if the calculation by this equation will give you a value less than the simple D value. And now you can see that L is the distance from the first bend and the ground level, which we say simple L. And let me take an example. Say that we have level 2 protection and 2 down conductors. And let me say that when we measure the length from the 2 points, we get simple L equals 5 meters. So if you go to the tables now, you will get Ki is 0.06, K6 is 0.66 for 2 conductors, Km equals 1 because it is air in between the 2 points. Now when you do the calculation, you will get 1.98 meters, which is quite a long distance, almost 2 meters. So you need 2 meters to make sure that I think it is not 2 meters. Maybe, sorry, I have to check my calculation. I think it is not 2 meters. It will be it can't be that much. Most probably it should be 19 centimeters. When I write it, I think I have made a mistake. So that there should be about 19 or 20 centimeters to avoid arcing. Okay, now imagine that if there is a catenary wire in between two poles, and if the grounding systems are joined together, two poles or 2 towers, catenary wire, and the grounding systems of the 2 poles or towers are connected by a ring conductor. And then KC value should be calculated from this. So there is no support from the tables. You have to calculate it. And L should be W/2 plus H. If there are no other buildings, non-symmetric buildings. Now consider that if there is a symmetric building comes in the middle, so that from the top of that building to the catenary wire, the distance should be greater than the minimum separation S that you will calculate by using this L value, KC value, then Ki and Km. Km is 1. Ki depends on the level of protection that you are adopting. And then if there are integrated, interconnected down conductor systems, the KC value calculation is little complicated. I'm not going to an example because of the timing problem. And that is all.